today we'll have the second lecture of Priyadarshi.
Right. Thanks. Okay. So this second lecture. So before starting today's talk, if there is any question from previous lecture, please you can feel free to ask me.
Sorry, for our benefit, can you give a 2-minute?
Yeah. I'll give a review. But if there are any question before that, okay. So last time I told you our motivation was understand holography. I will come into great detail in what holography means in de-Sitter quantum gravity. And I was telling you that holography is only property of quantum gravity, not any other theory. And for de-Sitter context, it was particularly interesting because holography always relates bulk with boundary. And global de-Sitter does not have Cauchy slice boundary. So that's why. Our question was, what is the fate of holography in de-Sitter quantum gravity? That was our motivation, one of the motivations. And today I will discuss the holography in great detail. So I was telling you that quantum gravity is very different than quantum field theory. Not only we are allowing the metric to fluctuate, like we are allowing some constant de-Sitter metric plus there is some fluctuation. This is one of the part, but also we have to impose the quantum gravity constraints because gravity is kind of some gauge theory. It has this local diffeomorphism invariance, and that leads us to these two equations, h psi equal to 0 and h I psi equal to 0. And I told you this is like kind of, so okay, let me draw a slice. So these two equations, they just means like gravity has some local diffeomorphism invariance. These equations means on the spatial slice, you can choose any kind of coordinates. So your wave functionals should be invariant under the spatial diffeomorphism. That guarantees this equation. And spatial diff, and then this equation, this guarantees like any time you can choose here. So that invariance is guaranteed by this equation, and we called this is Wheeler-DeWitt equation. And I told you that in de-Sitter quantum gravity, we have the vacuum always is always the solution, like the psi HH always over the constant. So when people study cosmological correlator, they actually study all the operators, all these operators, say they have some 1 or 2 in the psi HH. But now our question was, are there any other states which obey these constraints? So might be there will be a generalization of this kind of correlation function. Like we can take some cosmological correlator in some generic state which is not Hartley-Hawking, but they also satisfy the constraints. Our question was, do these states really exist or not? And I told you that yes, this kind of state exists, and we found this is something like e to the power is times z, and this is some like universal factor. It is some like local like functional, and this z can be non-local, and we interpreted that this z as some CFT partition function. I will come into great detail like how this is manifested today, and Z was satisfying these two equations, 2 Gij del Gij minus delta chi del chi z is equal to 0. This is just the Hamiltonian constant here. Is taking this form, and then always we have this momentum constant, which is this. This G is my metric field and chi is some minimally coupled scalar. And we were claiming like if you give me all the possible CFT partition functions which satisfy these two, oh sorry, it was actually not 0, it was some AD, Z, AD is non-zero for event D, it is some anomaly with some imaginary anomaly here. And we claimed like if you give me some possible like CFT theories and we can get some CFT partition function that will give me some possible states in the Hilbert space. Now, before going into today's talk, I just want to mention some subtleties here. No, Gij, everything is now on this d-dimensional space, like in the sigma. Like Gij is metric here. Like we did some like from d plus 1 dimension, we went to some d-dimensional space, like with some this Gauss-Kodachi equation. We did it last time, and this metric and field, everything is on the slice. This is some canonical way of like doing quantum mechanics. Okay. So before going into detail, I want to mention some of the subtleties. Yeah. No, okay. No, this is just like how we expand our metric in like, this is my square root of Gn. This is here, like this is some fluctuation on a fixed background. But what we obtained, there was no, like we did not like expand perturbatively our metric. We found everything in terms of this Gij. Okay, so I will come to detail, like what I will mean by Hij here. So there will be some Gij physical. This will be something like some sphere metric, because this one is the special case is some sphere. It will be something like with some good coordinate choice. It will be some square, and then there will be some omega square. This is some large, like because we are going to this. We are going to this large volume limit, so that will correspond to some large value of omega here, and then today we will expand this thing like kappa Hij. So we expand Hij around this large volume of sphere. But we will be not taking this kind of like Hij, say Hij2. This is some another expansion, another perturbative expansion. But for today's talk, I will only take this kind of expansion. So always there will be some big volume factor sitting there. So we will go to this large sphere and we will be studying deformation around that large sphere. I will come into detail today. Yeah, this is like how we will be doing this. Yeah, just some few subtleties. Okay. So that one point was this interaction. So last time we had this H gravity. Our full Hamiltonian constant is some H gravity plus some minimally coupled like scalar matter. You could take in principle any other matter, but we did not check for any other matter. For simplicity, we just have taken this scalar thing, and but also there can be some other interaction. And we have found that this structure, this psi equal to some e to the power is times j, this like in the leading order, this does not depend on your structure of H interaction. Okay. This is what we found, like there will be some dependence, but in the very subleading order of omega. Like I wanted to remind you like how we got this solution. We got this solution going to this large volume limit. Like we had this, okay, maybe some other chalk will be good. So here, like we took this omega, omega is kind of, you can think this omega to the power g is my square root g here, like so this volume of this Cauchy surface is related by some ddx of square root g, so this is some ddx of omega to the power d, and we took some large omega limit, and in the large omega limit this H interaction, they are very subleading. So in this structure they don't affect much. Now you could ask this question, like why this interaction is not entering into your wave function on the Hilbert space. So I wanted to say this is very consistent with what we know for flat space also. Like when we do like asymptotic quantization in flat space, like let's say I am studying massive fields. So this is my I plus, this is my I minus. So the interaction, they actually die if you go to this I plus and I minus, but still you can like find the full Hilbert space structure going into this large T limit. If you push to the very large T, you still get the Hilbert space structure. So for getting the Hilbert space structure, even if you lose this all the like information here, they are subleading, it is still very consistent. It is not like something wrong we are doing.
So here we do deal only with massive fields. Massless fields, there will be interactions which are present.
No, but you can generalize it. Like here it will be not. Like I am just giving an example. You can also do this for, I am just giving an example, like you can also do it for Sky Plus here. Sky Plus, everything is free.
Not in the presence of gravity.
No.
Let me 1 over r Coulomb like potential.
Okay. 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 I see. Okay. Now, okay, I just wanted to give an analogy. Okay, maybe then not massless field. Okay. Right. Yeah. No, I wanted to say like we are not doing any wrong. Like though we are like not having the information about the interaction here, we are not doing anything wrong. We get the full Hilbert space.
So from the Lagrangian point of view, the matter comes from some ordinary square root of g.
Yeah.
And lambda phi squared.
Yeah, it is some like some square root g, some del mu phi n square. Yeah. And there will be some interaction like of the matter. Yeah. But this is the but I am saying this will just determine all the structure.
Right, but there is a cubic vertex with the graviton and 2 scalars from here as well. If I expand g,
those will be there.
Those are going to be there.
Yeah, those will be
part of this.
Yeah, those will be part of. But I am saying if there is some extra part, those will be very subleading in omega. Like say I have some I wanted to say like because phi also has a fall off. Yes. This phi, this thing like they have, because these things they like phi goes as like some omega to the power minus delta times some O. So if you add more interaction terms here, like these are the free part almost, so it will be like a larger fall off. So they will not be appearing in the leading order of the solutions. Okay, so this is one comment. Like, this omega you can interpret as a large time. I will come to your point. And like this is something clock. I mentioned last time, but I did not explain.
You are disallowing interaction of the form say Ricci scalar times phi square.
Ricci scalar times phi square. Okay, they will be appearing, but they will control they will change the anomaly. Yes. Like this, like then it will be a different class of solutions even. Like. Okay, just another comment. Last time I did not actually solve this massive case. Like I just demanded my solutions are like some e to the power if, and if I told you it is some like x alpha minus 1 and dot there is some x0, and then there is some like part which is only present when there is some matter. There is some y beta minus 1, etc. And I told you, I claimed that you can recursively like solve this thing unless this x0 which will enter into my z, like my z is something e to the power I x0. But just one comment, like this beta you can find as some like d minus 2 delta. Delta is this like the scaling dimension of your matter, like how with large omega or large time your scalar field falls. So you see like, and this x alpha, this was like alpha we found as d. So you see like there is a two different series here. One starts from like this first series, it starts from omega to the power d dot, but then there is some another level which starts from like omega to the power d minus 2 delta, dot dot dot. Now, one comment is like if you turn on interaction, your delta can have some like correction. This is some like perturbative correction of your like scaling dimension. It can include. So now, but in the structure of psi, there is a level delta always. So you can like ask like what is happening if you have different delta. So now what we are saying that okay, you can actually take only those psis which have like delta after same delta after this perturbative correction. Like after perturbative correction you will get some delta. We will only take those sets of psi and make this our Hilbert space. This is some space of Hilbert space. Okay, this is one comment. So I wanted to say some, I can label my Hilbert space with this psi delta. This is one side comment because people often ask this question, like because delta can have some perturbative correction. And another comment, the last comment here, then I will start today's talk. That, yeah, I think what Justin was asking that whether omega is my time. So yes, like omega is my time, like I mentioned in the beginning of the yesterday, like last time's talk, like this canonical time was not a good time. Was not good because the Hamiltonian has no evolution with that. But like that's why we choose some clock. It is some, like you can think it is some intrinsic clock which was served by this guy, log of d dx integration over this omega to the power d. This was my clock. Okay, and we are expanding everything in large like time like described by this clock, that means large omega. That was our like understanding. And another comment, like last time I think Ananda you were asking about the probes. So there is another way of understanding de Sitter, like if you have some high energy excited state and then you can understand physics around those high energy excited states. So you can think like there is some, so here it is my de Sitter. Okay, it's not actually, okay, it's not actually any singularity. So okay, this is my de Sitter. So Penrose diagram you can think. You can now insert some high energy mass, you can just put some high energy mass and you can like study everything like with this high energy excited state. And what you can do, like this constant analysis tells us this, so this can serve as my observer, this high energy excited state, it can serve as observer. So the observer plus rest, they will satisfy the constant. The full thing will satisfy the constant. But if this mass of the observer or the energy of the observer is very high, you can like trace operators with respect to this observer. Like what I mean, like you can write some operators O which will commute with your I want to say with your constant the h, but up to some order 1 by epsilon, and you can actually perturbatively construct. You can actually claim like this is perturbatively exact, this relation. Like you can actually trace some operators with this like high energy excited state, and you can claim like they actually commute with these constraints. So so you can hide the effect of your this Hamiltonian constant and everything in this if you have some high energy excited state. Okay. Now, okay, some energy. I am saying some energy. It's like if your energy is high, you can hide the effect of the constants. Like that's what I am saying. And now, but the point is, this kind of way of looking is very perturbative. Like it is very perturbative. But if you like go in non-perturbative order of this epsilon, then everything will break. So that's why people ask this question though we have this gravity, we have this gravitational constant, everything, but around us we don't see like these constants are not very manifest. This is because we are living in some excited state, and perturbatively around the excited state we can understand everything very nicely. So so the constant does not like affect us. because we are seeing perturbatively around some high excited state, etc. So there is some like recent progress of this understanding. I wanted to mention some paper. So there is some recent paper by Marolf et al. Like they are like studying this perturbative construction around this de Sitter, and there is, I think last week there is some paper Marolf et al. 00111, and then there are some like paper by, so they are doing for de Sitter, and also then there are some work by in ADS. Like ADS, it is very well understood. This is some paper by Kyriakos et al. This is from last year, 2301.08753. So I just wanted to say this is some another way of looking at this this problem. Like we are not adopting this picture.
So this is like taking into account the back reaction of a very heavy.
No, okay. I don't think they actually include back reaction very seriously. It is very perturbative construct. Like it will break. It will just break. But the point is, you can you can hide the constant somehow, like with this. Like it is not very exact. It's not like very exact. It is some just perturbative constructions so that you can hide the information. Like this is almost like this when this like this mirror operator construction done by this Shufrod and Kyriakos is very similar to that construction also.
Sorry, I didn't understand. What does this buy you?
No, I am just saying this is another way of looking this thing. Like you are saying that there is some like whether we are doing on probe, I am saying it's not. Like I am just I will draw two different pictures here. One is like what we are looking at, what this way of looking. This is two different way. Like I am saying here, this you can hide the effect of the constant. So one is what we are doing. So I have say like in our paper we are kind of meta observer. So say there is some end like some de Sitter slice, which is the end of inflation, and we are getting all the information here, but we are some observer sitting outside. So Aninos called this thing like some meta observer. This is our approach in our paper, but there is this another approach like of doing this thing. So here like you are inside de Sitter space here. So you are in some time like geodesic, and your observer is here. Now you are studying operators around this geodesic. This is some another way of seeing de Sitter. So I am saying I am adopting this convention, not this. But you could also study this kind of like this is some equivalent way of description. But there you can hide the effect of constant by if you have some high energy observer, you can hide the effect of the constants. That's what I wanted to say. This is some like philosophical like viewpoint. Okay. So okay. Energy, like if it's like you can think it is some like if some high energy like excited state, it has some e to the power s is my density of states, so you can replace this e by e to the power s, and you can replace this also by e to the power s. Like how many states are there in this Hilbert space? You can hide the information in this precision. Okay, this is some like a different way of looking. Not necessarily on that time. I think you can. Okay, I am not sure, but I think you can look also around maybe. Not necessarily. Yeah, you can think some tube. Okay.
And why here you just look at arbitrary correlators?
Sorry, here. Yeah, here you can think like my observer is not actually interacting with anything like.
The correlators are valued at every point.
Yeah. This is some like more general. I'm saying these are two different pictures. I'm adopting this picture for this lecture. Like this is also like more suitable for understanding the inflationary dynamics, because this inflation ended somewhere, then there are some reheating everything, and then we are getting all the information. So this is another way of looking de Sitter. So okay, so this is some sorry. Okay, forget it. I think I have another check. Okay. So now I'll be talking about today's plan. So today I will understand jet this in a bit detail, and then I will go to some another basis, and then I will go to some non-gravitational limit, and this will, and I will tell you that Higuchi has constructed some states, and we found these states in the non-gravitational limit of our case. And then the last part of our like discussion will be this. So the Hilbert space is incomplete without any inner product structure. So I will define an inner product or norm in this space of states, and then this mode physics thing will come, like how can we interpret cosmological correlator. How we can understand cosmological correlator in our picture. Then I will tell about like whether they satisfy some holographic relation or not. This is my last part, and then I will give you some outlook. So this is plans of today's talk. Okay, let me start. Okay. So I can just is there any question? Please stop. Feel free to stop and ask me. Yeah. So last time when we found the states psi equal to some e to the power is times z, we did one perturbative expansion, but that perturbative expansion was in this omega large time. We did not do any expansion in kappa, the square root of g Newton. Today I will do that expansion. So so this is my picture. So we went to this very late time here, and now my this physical metric here is something like 4 omega square 1 plus x square so this metric, this describes some like sphere metric, and this omega large means like we are taking some large volume here. This is some unit sphere metric, and with this omega is my size of this sphere. And now this is the perturbative expansion we want to see. Like this is, you can think like some deformation around some large like sphere matrix. You can think like that. Now the point is, before doing this kappa expansion, we can always sorry. Yeah, x is my this. You can think it is this. This when you write a sphere in terms of this this coordinate, this flat this coordinate, you can think like this is my coordinate on this Euclidean like slice. So yeah, so I'm just writing a sphere metric with this coordinate on these slices, like on this flat slice. 1 minus, okay. Okay, might be, okay, might be, I have to check. I thought it is 1 plus, but okay, I'll check and I will tell you maybe later. Okay, there is a question. Okay. Now I just wanted to say I am just writing in these coordinates, and then what I wanted to do, but like with this going to these coordinates, okay, let me say nicely. Like we saw that this Z is almost like Weyl invariant. It captures some Weyl anomalic term, that's okay, but like when we will be calculating some like inner product everything, we will have this mod psi square, which will have this small j square. So Z is almost Weyl invariant. So by cost of an Weyl anomaly, we can actually absorb this full factor and go from this sphere to this flat space. Like I am just saying, my metric was this, like this. This is my metric, large metric is this here. I am now doing a Weyl transformation, and now my metric will be some changed metric. I will work with this, some delta ij plus kappa ij. Is this step clear? Like, but I am saying, yeah, there will be a cost of an Weyl anomaly because this that will capture. But for just this analysis will be simple in this flat coordinate. I am saying it is some like flat Euclidean coordinate, and then there will be some kappa expansion. Okay. Okay. Now after going to this coordinate, this is just for some simple analysis. You could do in any coordinate like this. It's in your hand, but just for simple analysis, the result will come very simple here. Okay. Now, after going to this coordinate, we can expand this partition function. Okay, what is the time? This is something like exponential. There is some m copy of this guy and some n copy of this guy, and this functional, like I told you, like this, all the e to the power is, these are all my some local functional, but there is no bound on z. So z in principle we have some like non-local functional, and if we demand this is some partition function, so it will be natural to expand these things, these partition functions, with like this j and m 1 by n factorial n factorial. So I am writing some coefficient function. So the y will be function like the argument of the h. So I'm just writing some general expansion here. Okay, I can follow this level. So there will be some in like metric fluctuations, in, jn, and a function of yn, and then there will be m copies of matter fluctuation. I am just expanding this z with some kappa. Okay, there's nothing more than that. Now, I told you that z will be some equation, and those are like sign of this CFT partition function equation. So we had this equation for like this 2gij del gij minus delta chi del chi acting on z. This is my some anomaly times z, and then there is this hij is some 0. Now I have expanded z with some coefficient function with some matter fluctuation and metric fluctuation. Now this identity will have effect on this coefficient function. If you just put this differential equation, they will have the effect. And what will be the effect? So the effect will be, this will give me some trace identity, which will be some one like in n plus 1th order coefficient, and its trace, like I want to say ij, and it is something like other ij, say i1 j1. I am just tracing over only one factor, and then there will be some I2, J2, etc. This guy will be related, okay, there's no space here, will be related with, will be some function of the one lower g. I means like it will be, if it is n plus 1, the trace of n plus 1 will be related to some function of gnm. That guarantees this equation. So there will be some word identities of this gnm function that relates the trace of gn plus 1 with gnm. We call this word identity as trace word identity. And then also there will be some diff word identity, which will be relating this divergence of gij n plus 1. Okay, there will be some other index I am just saying. So this identity hi acting on z, this will relate the divergence of this g coefficient, one higher order to one lower order. It will be some function of some gnm. So this is just the effect of this constraints. So I want to remind you, this came from the Hamiltonian constraint, this came from the momentum constraint. I am saying the effect of the Hamiltonian constraint on this coefficient will be manifest with this trace word identity, and the effect of the momentum constraint on these coefficients will be manifest by this diff word identity. Now, we all know from our course from string theory, like if you do some diffeomorphism, you can also compromise, like you can also compensate that diffeomorphism with some Weyl transformation, and that will give you some CFT. So if you particularly transform this, if you manipulate this, so I had this. Okay, I can delete this part, I hope. So there are two identities I got. One is trace identity and one is diff identity. But there is another identity which is a combination of trace and diff, and that is just some conformal word identity that we all know for d dimension. So this conformal, then there will be some conformal word identity that will restrict this individual Gij. Okay, that will restrict my individual Gij. There will be some or differential equation equal to 0. This is my conformal word identity. This is all know. This is a standard conformal word identity with particular choice of anomaly here. Word identity. So I want to mention these things because it will be like useful to understand the physics with this identity, like it will be crucial, these identities. So I was saying the effect of the constraints you can understand as some identities on the coefficient function. The coefficient functions appears inside the jets. Up to this everything is clear? Okay.
One clarification is that these coefficient functions that you have, those are hiding derivatives as well?
No, these are, okay, so you are saying whether this is some conformal correlation function, and you are saying whether it is conformal correlation function of some like del of phi something.
Yeah, I was wondering why should it be local in or just
okay.
powers of each and not also involve derivatives?
Okay, this part we don't know, but we found like this is almost like I will tell you like what this from this identity one can write this Gij_nm is just same as this guy. Like from this word identity, it will be just, if you write this word identity, it will manifest. Like this is just some stress tensor correlation function. Like. And then there is some scalar field phi. This phi is some dual dimension of my chi. Chi was my scalar field in the de Sitter, but I am saying this G, you can think as some like correlation function of some CFT with in the background metric Gij, and if you calculate this correlation function, I am claiming that this correlation function will satisfy all these identities. This we have found. So this is some, and this phi, this okay, this I can delete this part. So I am saying this phi is some dual dimension. It is some what is this? Okay, it is some, I think, d. Okay, it will be some d minus delta. And where this chi was, for chi my dimension was delta. It will be just some dual dimension d minus delta. And this is some like auxiliary field. We don't know where this exists. So our algorithm is, if one gives you some CFT correlation functions, which over these word identities, this is some set of tools you can think. And then you just calculate this GNM, and then you club them together, you put them inside these jet functions, and then you get the states. So this is our like way of thinking. We are not saying this CFT lives somewhere in the boundary. We are not saying anything like that. Okay. So yeah, this was our understanding. So yeah, sure. Oh, okay, sorry, I forgot to write it. It is every M. I just wanted to say the structure was the like one, but this trace always relates one higher n to one lower n. This word identities. This is the structure, very generic structure. One can get. Okay. Sorry. Oh, this trace identity. It is like as I mentioned last time. Like this is something like imaginary, and this is. Like only non-zero for even d. So this you can think like for 2D, it is some like analytic continuation of this Brown-Henna central charge. For 4D there will be some other combination, but also imaginary. Yeah. So okay, I just wanted to clarify our slogans. So our slogan is, if one gives you this kind of CFT correlation function, set of CFT correlation function, like I am giving you some Gij nm, then I can club them together, write a jet, and that jet will give me a good like wave function in this de Sitter Hilbert space. That is our claim. Like you need a sets of like not only one function, you need a like whole bunch of them, and then you can put them together, write a jet, and that will be our wave function. Okay. So now I just want to go to another basis which will be very useful for understanding this different physics like non-gravitational limit, etc. Up to this.
That is a physics theory. And it's stress tensor. You know all the correlators.
Yes, yes. No, but also you have to check the anomaly. There is this anomaly. This CFT. There will be some anomaly term here also. This square. But that anomaly should be imaginary. Well, because that was our constant on J. Okay, one nice way to think this thing. Okay, you think from ADS CFT, you have this some Euclidean radius. Go to the boundary. Like that's how one calculate the Hadley-Hawking.
That's easy because you just change the sign of the kinetic.
Yeah.
That will make it imaginary.
So there is some set of correlations one can give.
One can give. These are like standard. Yeah. Now this will you can think these are like some this will be give you some wave function, but you can start with the Hartley-Hawking of a particular theory of Hartley-Hawking a different theory that will give you some different, like I wanted to say, like you can add now the states, like you have now the partition function, you can add this two partition function, get a new partition function, and this is also some valid state. And the one particular interesting point is there will be some cross terms now. So I am saying my states are kind of this thing. So if you calculate some like correlation function in this side, there will be some cross terms between Z1 and Z2. That will be something new for cosmology. Like people always compute like this kind of thing, like with a particular Z1, this thing. But now I think there will be some new like ways of looking at this cosmological correlator. Like. Does it answer your question or?
No, I mean, okay, suppose I just want, suppose you do that kind of, there is a well-known theory, which you know, all the stress tensors and all the stress tensors, all the correlators, you evaluate the wave function.
Yes.
You evaluate the cosmological correlator.
Yes.
What is the sort of?
No, this will be.
Some example.
Yeah, this is just the Hartley-Hawking. I am saying Hartley-Hawking of a different theory. You can think, like.
Explicitly understand those cosmological correlators. I mean, just it's a.
Yeah, I think one can. Some of my friends at ICTS, they are doing it. Ashik and Tunir and they will be. Not free theory. I think they are doing they are like building all these 2-point, 3-point, endpoint cosmological correlators, and they are writing it explicitly. Like this we are giving some picture, some big picture, but yes, some formalism you can think. But for explicit relation, I think they are doing it now. They are doing it now. Yeah. But this is some like big picture I wanted to give. Yeah.
Sorry, I thought let's try to make your premise a bit more mathematically precise, and you should correct me if I'm
Sure.
this wrong.
Sure.
So your motivation was that you want to find a solution to the Wheeler-DeWitt equation, which wasn't really the Hartley-Hawking wave function,
Yes.
but it had some dressing factors on top of that.
Yes.
And then you wanted to solve the Wheeler-DeWitt equation with the dressing factors.
Yes. That will just come after choosing that basis. It will be explicit.
So you will get a class of wave functions which satisfy the Wheeler-DeWitt equation.
Yeah.
Which is not just the Hartley-Hawking.
Yes.
So that is a mathematically.
Yeah. That means yeah.
Now the next thing, what we have been saying is that the solutions can be rewritten in terms of the c to the power is times z, and the z you want to interpret as the partition function of a CFT.
Of a CFT. So different CFT will different
CFTs will give rise to different solutions.
Yes.
For this, right?
Yes.
So till now, this is here. Now, I guess the question is, because you have this flavor that this is like a DC to CFT correspondence. So I think this is where the statements are not very precise. Is that correct?
No. I am saying it is not from the DC to CFT. I am not claiming these are like actually a CFT. Only CFT is here, like there satisfies the word identities. If you,
so
but
it's a solution to the Wheeler-DeWitt equation.
It's just this set of function correlation functions. Right. That's it. We are not claiming anything more than that.
Right.
There will be some other constants, but we don't know this constant. So you can put a quote unquote CFT.
Yeah, exactly.
Yeah,
so I think putting a CFT in quotation mark.
Yeah. That's yeah. I am not saying it's a CFT at all. Yeah.
If you have this formalism like this, you should work out an explicit example.
Yeah, I think my friends are doing those things. Yeah, their paper will be out soon. I think this year, hopefully. Yeah.
So he's going to give us a prescription to calculate general class of wave function.
Yeah. Like we are saying, okay, there is this huge debate whether there is one wave functional or there are like different, like when we put this paper, like there is a huge debate whether there are really many states or only one state. People always believe like there is a full quantum gravity we don't know, and that full quantum gravity will fix just one state. That's the belief of people. I don't know.
So de Sitter is associated with some entropy for the horizon, right?
Yeah, that's.
So if you wanted to account for the entropy, don't you expect?
No, it may be finite. Like what if there is some entropy? Like what we are getting is some like infinite Hilbert space, but there will be some other correction or something that will give us finite. But also there are some other people who claims like there will be only one single state because there is only one consistent full UV quantum gravity, and that will discard all the states. Maybe there will be like all the states we found.
Who are such people?
Okay, I don't know. There is some folklore. Okay, I don't want to. Okay, I also don't know the names, but there are these cosmology people I wanted to say. Okay, because everything is recorded here.
So they are saying that there is a unique quantum theory of gravity which is going to make the entropy of de Sitter space finite. Is that what you said?
That you can think like, okay, entropy finite means there are only finite number of states. That is one conjecture. Like people say, okay, this is your structure of space, but this may not be very appropriate. There are some other constraints which will give, maybe this, I will give you this inner product. So now I did not talk about the inner product. So so this inner product structure, I will, so how much time I can have today? I just wanted to.
You can go till 4 o'clock.
Oh, okay, very good. Okay. Okay, sure. Okay. Now, just point is, you can maybe we will define some inner product. Maybe if you analyze the inner product very precisely, maybe you will get some finite structure of your Hilbert space. That's our understanding. But also there are some, I think, like the cosmology people, I think they actually protested our against our this construction. They said, oh, there is only one state, and they did not agree with us, I think, when we put out this paper. So yeah.
So is the protest because somehow the wave function is supposed to carry the information about this cosmological correlation?
And
if there are these multiple wave functions, there are multiple answers.
Yeah, there are multiple answers. So I think one have to make precise like what you observe at in inflationary cosmology. What you observe, I think we have to make it precise. But this is some generic. Huh? No.
Also generating something of the cosmological correlation.
Yeah, that's the that is the vacuum, because that you can get with some Euclidean path integral. Yeah. Now the question is like, I think Hartley-Hawking in their original paper they also mentions this thing like you can get also other states, but this is the other states we are prescribing. Like. Yeah.
But the other states satisfying H psi equal to 0, not adding anything to the right hand side of the equation.
No, we are not adding anything to
Then it is the same as the Hartley-Hawking.
Yeah, there is no notion of energy here, so you cannot say it is like minimum energy or something.
So I think it literally means that if you calculate the spectral index, you can get two different answers. Am I right?
Spectral index means?
So suppose you calculate the 2-point function of scalar perturbation. So there is some way of relating the wave function to that calculation.
Yes.
So in principle, you can get two different answers.
Yes, two different like wave functions will give two different like 2-point correlation. Okay, but we have to make it more precise with relating like at least lower point cosmological correlation. Yeah, that's I think.
Answer in that case, if they really have a sort of continuous class of wave functions, you need to average or you need to integrate.
Yeah, this is the mathematical statement we are getting. Yeah, so we have to relate with the real physics. Yeah.
So making it precise means in a sense you have to calculate the different CFTs and calculate the.
No, he has to make precise the recipe for calculating cosmological correlators. Starting from the wave function.
I will give you a prescription how to relate cosmological correlator, but for explicit calculation, we have to still wait. Yeah, I will give you some recipe like how to do that.
The answer will be some kind of average.
No, you can think you can. You can think like also superposition, or you can think with also one state. But that's different than the Hartley-Hawking. You can also calculate. But I don't know, like what you observe will be, might be some, yeah, might be superposition. Okay, I don't know. I don't want to. Okay.
So far, your calculation is clean. I don't see any problem mathematically. So
Yeah, everything is very consistent. Like we did not go to Euclidean radius also anything. Like for getting explicit Z, you have to do that. But the solutions are like we did everything in de Sitter. Yeah. Yeah. So just one small comment here. Like I was telling you, like when we impose this quantum gravity constant, like if you take some, say you have some ADS space. Okay, you have some ADS space. If you put some excitation here, say I am putting some excitation in the bulk. So I say I am putting some operator phi, and if you get this phi on top of vacuum, these are not going to satisfy your constraint. But one way to make this like this state satisfy the constraint, that you have to dress this thing with boundary, because in boundary there is no this gravity dies, so everything is very well defined. So you collect a Wilson line with the boundary, and then this guy is very well defined. You are dressing that state with respect to boundary. That is a general understanding. Now, so you could ask in de Sitter, like whether you can understand our state as some dressed version of some QFT state. Okay, so that's the question. But now the question is, there is no boundary here. So now how to understand that dressing? So no, I think this is draw some geodesic, which is some like this is how one draw some Wilson line in gauge theory also. Okay, there's some paper by Giddings, I think. But I also have not seen, but this is the understanding I am saying. It's just like gauge theory, you draw some Wilson line, but here you cannot draw some local Wilson line, because there is no local gauge infinite operator gravity. So these kind of things are barred, but still you have a boundary, and with this boundary you can dress, I am saying. Yeah. So that is, but I am now asking the same question in de Sitter. In de Sitter, there is no boundary here. Like this is my Cauchy surface. Now, how to understand the dressing? That is my question. Now, I will give you a recipe for that. Before that, I want to rewrite this Hilbert space in a different basis. So, let me tell you how. So, if you remember, I was working with this Carly G, and this Carly G was this coefficient function and times this metric fluctuation, and it is integrated over. Metric fluctuation, matter fluctuation. This is some like functional. These are my coefficient G. This is some fluctuation of metric. This is some fluctuation of matter. This is my wave functional, and our Z was something like, okay, there is some G and M factor also, and then this M copy of H, and there is some M copy of chi. Now my wave function was some kappa to the power n, G and M, something like that, sum over. This is my wave functional. Now I am saying, take two different CFT. So I am naming them by this one and then this one, and I am putting a factor lambda here, and I am just taking, so this is some, if you give me some G coefficient correlation for this G, I want to remind you this is just some CFT correlation function. And so if you multiply with some metric, integrate over those metric and this thing, you will get a functional. And I am telling you, tell me two different CFT functional which satisfy the same anomaly. Take a convex combination of them, lambda can be anything, and I am parameterizing as G lambda. And I am claiming, because of this choice, you can see like these are satisfying the same word identities because of this particular choice. Like there is some lambda coming here, and that lambda is getting cancelled here in the, because all these word identities, everything, they have this anomaly term here. So in this particular choice, I am claiming this is also satisfy the same word identities. Okay, this is fine. Yeah. Two different. So the NM index are here in the below. Okay, you can think. Sorry, I write. Linear combination, but a particular linear combination, because you have to also take care of the anomaly. Some convex combination. With this particular combination, that anomaly becomes like the same. It satisfies the same equation with the correct anomaly.
The same anomaly.
The same anomaly, yeah, same anomaly.
So you can think of it as a
Yeah, same. It's not same. It's the same another solution of your word identities.
With the same central charge.
Yeah, same central charge. Yes, yeah, same central charge. Yes, like same anomaly with same central charge. Yes. I'm just claiming like this is another solution of your. That's what I'm claiming. Yeah. Just now I will do a like very basic thing. Now I just you can write this thing explicitly. So what I am doing, so I have this for the full picture I am writing the full solution what we had e to the power I is, and then we have this exponential of kappa to the power n, and I am putting 1 minus lambda. This is my first G0 is my first like wave function for the first CFT, and then I have a wave function for the different CFT. Okay, this is I am saying this is also my solution. Okay, now everything is linear here, so you can think like this is also my solution. Okay, because this is also a solution, and you see this actually gives me something very nice, which is there is some sum over a name kappa to the power n G0 G0 nm minus this G1 nm times let's say I am expanding everything in terms of G0. So if you put lambda equal to 0, so it will just capture this guy. So it will be some exponential of sum over n of nm kappa to the power n G1. Okay, so if you think this times this is my some initial wave function. Okay, so you can think this times this is some e to the power is times some z, this is. So I am writing this some psi 0, and then you have a structure in front of psi 0, which is just this kappa to the power n curly G0 nm minus curly G1 nm. Okay, this is the structure. Okay. Okay, so this is some another basis of writing. So what we are doing here, just want to draw a picture. Like you can think there is a landscape of space. Okay, landscape of this theory space. Say this is my some CFT 0, and this is my some CFT 1. So that means I have this some everything in terms of this curly G0, and here I have everything in terms of this curly G1. Now if you draw a line here, this line you can think it's some like tangent vector from one CFT to like in this vector space, and this tangent vector is like written in this way. So you can think this is another way of writing the same Hilbert space. In the it is some like tangent space. You can think like that. So if I write it explicitly, you will see a nice structure, which will be okay. I want to write it very explicitly. This will be something kappa to the power n, and then there will be some Gij nm minus, sorry, it is Gij nm but for theory 0. Okay, I think I messed up the sign here. Okay, sorry, minus here plus here. I think, yeah, sorry, I messed up the sign. So it will be 1 here and 0 here. Ij nm, and then there will be this n copy of this metric fluctuation and this m copy of this scalar field fluctuation here, and now on top, and this is all integrated over now. This everything will be integrated over here. Okay, let me put the integrated sign here. Okay, this is sum, so it is integrated over. We are integrating over all these fields, so it will be some y1 dot dot and z1 dot dot, and then there is psi 0. So you see, this is almost like there is some ground state. This is my, you can think this reference state here. This is my ground state. Like you can think this is my Hartley-Hawking. You can replace this thing as my Hartley-Hawking. So what is happening here? So I want to like look at the structure. So we are putting some excitation on top of that, and we are also smearing. Like this will be some function of this y. Okay. Yz, and also this will be some function of this yz. Okay, So we are integrating over this all the yz variables. So we are putting some excitation and we are smearing with some function, and that function has to be some difference of two different CFT correlation function. And not only that, you have to also dress it. Dress means there is an infinite sum here. There is a sum over n and m. And this guarantees you that these states are satisfying these these Hamiltonian constants. Like the Hamiltonian constant, there is this diffeomorphism identity and word identity. If you just truncate this sum, that will not gonna satisfy these identities. Okay, this diff-and-Weyl identities. So that's why I am interpreting like there is this sum. I am like saying like this is kind of like dressing the states. So this will be very clear if we go to a non-gravitational limit. So this is my full answer of the gravitational state. This is another way of writing which will like make the physics very manifest.
Sorry.
Yeah.
In the example that you are showing, there are two CFTs.
Yeah, there are two CFTs.
But in principle, that could be a convex combination of CFTs.
Convex combination, but when we took, yes, sure. Yeah, there will be convex combination, but with this derivative, I got rid of that lambda. Because everything is linear, so you can take a derivative that with respect to lambda, that will be also my solution. So I got rid of that lambda, and I got this difference of these two CFT correlation function, or these two CFT polynomials, these functionals here, and then I am claiming that you can think this is my smearing function, but smearing function is a square integral function or anything. That has to be some CFT correlation function, difference of two different CFT correlation function, and you have to also make a sum. Like I will come to the non-gravitational state. That will be, it will make it more clear. Okay. And then it will be some psi 1. It was psi 0 for my case. It will be some psi 1. You can expand around any basis. That will not matter anything. But I am saying this is a way of looking the same Hilbert space in this tangent space, or we call it also small fluctuation basis. Some small fluctuation around this vacuum that will be covered with this like relation or of this expression. Is it fine?
But getting rid of the lambda was just a matter of convenience?
Yeah, just a matter of convenience. Like it will be easier to understand the non-gravitational limit. I will tell you like how. Like it is another way of looking. You can also work with this like different jets. But I am saying in this way of looking, the physics will be very manifest. Like taking the non-gravitational limit, relating to some old work by Higuchi, it will very manifest. And it will also tell you this old puzzle. Like I was telling you, like in the beginning, if you add some excitation on top of Hartley-Hawking, that is not going to satisfy the constant. But if you look in this way, you are doing some smearing. Smearing is a particular choice of smearing, and also you are like making a sum over n and m to satisfy this diff and trace word identities. This is my good solution of this H. This will make our like understanding very like manifest. Okay, that's what I am claiming. This is another way of looking. Okay, so now okay, I wanted to write this thing in a nice way. Okay, I can delete this thing and but I just wanted to copy this answer. It will be like it will be needed for us later. So okay. So I am saying this is my possible state here, and you can also think it is kind of some n particle excitation on top of Hartley-Hawking vacuum. You can think like that if you want to think. So I am saying this is my good state in m kappa to the power n, and this g n m, and there is this y vector, z vector. It's a function of y vector, z vector, I vector, j vector, and I am integrating over hi1, j1, y1, chi z1, and then I have this psi Hartley-Hawking, or you can think it is also psi 0. So I am saying this is my, okay, and I am replacing it delta g. I am not writing these two different things, I am just replacing with the delta g. It will be understood like it is a difference between two CFT correlation functions. I'll tell you, when we will be getting the non-gravitational limit, then it will be very manifest. There will be a tail of like excitation we are adding. Like when we do dressing, you can also think like that. It will be very manifest. Just give me 1 more minute. Yeah. So sorry. Okay. So now Now I am saying take 2 CFT, quote unquote CFT. I don't want to say. Okay, so then this is like something say this is some G1 NM. There are all the ij factor I am hiding, and then this G0 NM. And then I am saying these are all equal for n less than n0, and this is also equal for nm n equal to n0 but m not equal to n0. So only from that n equal to n0 and m equal to m0 the non-zero difference come. Like the delta G only becomes non-zero after these two values of your this sum. It will only start non-zero. Then you can do a trick. What you can do, okay, I can delete this line. What I can do, I have this state here. I can just divide by some kappa to the power n0 here, and so that will give me some kappa to, that will only cancel this kappa to the power n0 here. All the before term is 0, but all the higher term kappa to the power n plus 1 term, that will be order kappa, and in kappa goes to 0 limit I will take this limit kappa goes to 0. So I am truncating this sum basically. So now my state will be psi this thing. Okay, this is my psi ng. This is something, then delta G n0 m0 okay, and there will be all the integration over y and z. Okay, I can delete this part I hope. So just look.
I got a bit lost. So this capital G is related to the partition function, right?
Yeah, this is the capital G is the correlation function.
The correlation.
And so my notation is okay. Yeah, my notation is confusing. This curly G is my functional. So I am writing my J is something like e to the power some sum over kappa to the power n curly G n m, and then in the curly G there will be some coefficient function. This which is some almost like some CFT correlation function, and then there will be some fluctuation here and the chi. So here
So here you are making a choice of
CFT that will give me some non-gravitational limit. Like I am saying, only non-zero contribution comes after n equal to m0 and n equal to m0. So if I can divide by this kappa to the power n0, and then I will capture this term. All the other term will be order kappa, and kappa goes to 0 limit, they will be gone.
So what enables you to make this choice? Is this obvious that you are allowed to make this choice?
From the word identities, there is no restriction. Like from the word identities, there is no restriction. I have checked from that, but still, as we don't have any other constraint, so this I hope this is like we have a lower point function same, like 2 CFT. The lower point functions are same, but they are differing from some higher point function. Like you can think like that. You can always make this kind of quote unquote CFT. So that. No, the point is the other terms for n less than n0, this coefficient is just 0. This is a delta. This is just 0. Okay. So yeah, this is fine. So I wanted to like look at these two different things. So I am claiming this is my non-gravitational limit and this is my full gravitational limit. So I can tell you one more thing. Like this is some CFT correlation function, quote unquote CFT, and I will tell you like this CFT have this algebra like this SO. No, phi ng will not satisfy, but it will satisfy something else. I will tell you just like this. Okay, let me. Yeah, thank you for the question. Yeah, so I am telling that this psi, the full psi, that will satisfy the Hamiltonian constraint, but this psi ng will not be satisfied by the Hamiltonian constant, but it will satisfy something else. I will tell you in detail. So this is our CFT, and this CFT algebra here, this SO1, D plus algebra, SO1, D plus 1 algebra. This is same as this de Sitter isometry algebra. isometry algebra, or this is some Euclidean CFT. Euclidean d-dimensional CFT algebra. This is S1, d plus 1 algebra. But you look like what I demanded. This will be something like this. This delta G. This will be some difference of two different CFT correlation function. But both the CFTs are some like dual they are constructed with some dual operators. Like here, like delta G. Okay, let me write it in a nice way. So this guy, this is something like some T stress tensor dot some phi, like n copies of stress tensor, n copies of phi, and their difference between two different CFT. Now the point is these changes under SO1, d plus 1, but this phi has some dual dimension, d minus delta, and also these fluctuations, they also change under this SO1, d plus 1 algebra, but as they are dual to each other, they compensate and they make this under full SO1, d plus 1 algebra, the full thing is always invariant. This thing is always invariant. This psi h is always invariant by the symmetry of your de Sitter. So I am claiming these guys psi ng, they are the solution of the integrated constant. Integrated constant, what I mean here, like you can, so this de Sitter has some like this isometry, like this, if you go to large time, like you can have this, like this Killing vectors with a very large time, and these Killing vectors, with these Killing vectors, there are some component like xi0 and xi, and you can make the isometric charges. What are the isometric charges? The isometric charges are something just integrated version of your constant. So you can think it is like xi0 nh plus ni hi, xi hi, given a Cauchy surface sigma. You can make some isometric charges, and by definition they satisfy this algebra. Isometric charges satisfy this SO1, d plus 1 algebra. So I am claiming, like though this psi ng does not satisfy this Hamiltonian constant, but they satisfy this guy. Okay. Sorry. This is my definition. This is my. No, this is my Cauchy slice. So the charges are like integrated over this spatial region. Charges are always like integrated over the spatial region, and the spatial region I am choosing this Cauchy slice, and this is my definition. You have this pointwise constant. So these are, you can think these are some weaker constant. This is like at each point of the Cauchy slice, these constants are valid. This is a very strong constant, and that's what we solved for. And there is some weaker version of these constants, that is this qi. And like we are studying the states, and like what annihilates, like what are the states which are annihilated by this qi, and those are the psi ng, and those are this where you truncate this sum. Okay. Now from here to here you can think, if you have some psi ng that does not satisfy the constant, but if you want to go from here to here, you have to dress it. Dress means you have to add all this higher order of n and m, which will give you the consistent solution of that word identities. Like otherwise, if you don't have the sum, that will not gonna satisfy this diff-and-Weyl word identities, because if you remember, the sum relates one higher order to one lower order. So sorry, the word identities, they relate like this word identities, they relate gn plus 1 to gn. So if you make some non-zero gnm here, say I am studying this thing and I want to see whether they satisfy the diff-and-Weyl anomaly. Sorry, diff-and-Weyl the identity. Now because you have already some non-zero gn, that will always generate some trace and divergence of gn plus 1. So if you have this term, if you put in this identity, that will always generate one higher order gn plus 1. Is it clear? Like I just. Like I wanted to say, like these identities, they actually relate one higher order to one lower order. So if you just put this non-gravitational thing, and whether you want to check whether this will satisfy these identities, that is not going to satisfy. because that will this identity will always generate some one extra term here. Like if n plus m is 0, then that always says n plus 1 also is if n is non-zero, then that will also give you n plus 1 is non-zero. Yeah. Yes, sorry.
So psi there was satisfying this Hamiltonian constraint.
Psi, this big psi satisfies. Yeah.
Big psi satisfied.
Yeah.
And now
I made some limit.
This is something of a toy example.
Yeah.
Which actually did not satisfy this Hamiltonian constraint, but satisfied some weaker version.
Weaker version of the constraint. Yeah.
And then, but why are you doing this at all? What is the logic? Why psi?
This will be under. Okay. This is some. Okay. One way of one motivation was like Higuchi did some construction very earlier. Like he did some group average states. Like he said he wanted to satisfy this equation. Okay, psi qj equal to psi. Like what is the solution? So what he heuristically did, he just averaged over de Sitter group. He took some QFT state, he averaged over the de Sitter group, and he found the solutions. And what we are saying, this is just some one candidate for Higuchi states. We wanted to like relate to our old literature. That's what one motivation. Yeah, we actually don't needed this thing, but this is like to, because Higuchi already had some work, so we wanted to like think like whether we are getting the same solution in some limit. That is what. So I was saying like from here to here we are doing some ng limit, and here to here we are doing some dressing. You can think like though we don't have any boundary or anything, but still we can add some terms such that it satisfies these word identities. Okay, if it is clear. Okay. Now this is n curly h and ni curly h. N is my this lapse function and shift function, and this is a Hamiltonian constant and momentum constant. There is no? Psi ng does not have, like, yeah, I have taken some limit of kappa. Yeah. Yeah, you can construct that Higuchi did. I am saying that Higuchi did. Higuchi what he did, okay, I don't have much time, but Higuchi took some QFT state and then he averaged over the de Sitter group. We want what? Some de Sitter invariant like state. This qi, you can, if you like exponentiate it, you will get some u, which is the action of your de Sitter group on the Hilbert space, and you want some state which satisfies this. This u is the element of your de Sitter group. Like so now, what Higuchi did, he took some psi QFT and he took some like representation of your this de Sitter group, and he averaged over the full group. Now by definition, if you act with another u on top of it, you can always absorb this u. Like I am saying, if you act with some u prime, you can always absorb this thing because you have some invariant hard measure. So you, by definition, this is going to satisfy this equation, or this is going to satisfy this equation. This is the charge, this is the group element. So Higuchi constructed this thing long ago, 1991. And but what I am trying to say, like from our construction, you like this one problem with this, it is very difficult to do this thing. Like I think it is only done for de Sitter 4 or de Sitter 2, like, and it's very like mathematically problematic to, like, it is very mathematically rigorous, like you have to take care of many things, but I am saying this is the easiest way to construct this kind of states. Okay. Okay, so okay, sorry, okay. So these are all the states. Now I think I have some 45 minutes, okay, maybe 40 minutes. I will, now I'll come to the inner product. Okay, so this, so our Hilbert, so as you know, Hilbert space is incomplete without inner product structure. So I will just briefly review to the inner product, then I will come to cosmological correlator, and then I will briefly comment about holography. Yeah, so, okay. Just, okay, great, thanks. Okay, so the inner product structure will be very like very straightforward. Like This is the same like we have done for string theory or any other gauge theory. So I am writing the structure of the states like psi qg or the full psi. This psi will be full psi. This will be something like kappa to the power n delta g nm. There will be sum over n and m, and then there will be some basically some base state. You can think this is some Hartley-Hawking or some Z0. I am writing some Z0 g chi. Okay. Now I want to build some structure like this, inner product of or norm of the two states. Now it will have something like I'll have some measure dt d chi, and then I have these guys. So there will be some n kappa to the power n plus m. So there will be n m, n prime, m prime. There will be two factor. One is this. So this delta g is a difference of two different CFT correlation function, and then there will be something like n m, and there will be some delta g n prime, m prime, and then there will be this square. Now the point is mod z0, though it has a Weyl anomaly, but mod z0 square does not have. Like z0 transfer in one, it is imaginary. So z0 transfer in one direction, z0 star transfer with a minus I. So this guy does not have any Weyl anomaly, and these things are not also carrying any Weyl like anomaly or anything. And the measure can. There is a subtlety there. I want to emphasize, but up to that you can you can define some structure here, and I am claiming this integrand is almost Weyl invariant. So you have to divide by this volume of your diff-and-Weyl group. Okay, with some there will be some numerical factor. So I am saying this is my proposal of norm. In this space of states, this is my proposal of norm. Okay, this is just like any other gauge theory or even string theory. We did this thing. Yeah.
Is this non-finite?
Yeah. Okay, we have checked like there is no, like we have regulated this volume. So this is the infinite volume. We have regulated this volume, and we have to do also zero mode fixing. After that, it seems to be finite. I will come into detail, like how I will explicitly write this norm. Okay, and then yeah. Okay. Now, as you all know, like to explicitly write this norm, we have to do this Faddeev-Popov trick, and for that we have to choose a Faddeev-Popov determinant, which will be like identity equal to some Faddeev-Popov determinant integrated over some d xi. Xi will be the diffeomorphism along this. So I have these slices sigma, and my like invariants are under some xi here. Like xi will be defined by giving me some diffeomorphism along the slices, and there are some Weyl parameter phi. Phi will give you the Weyl transformation, and then so I have this. I have to introduce some gauge condition. This is my standard Faddeev-Popov trick, like we all do for string theory or any other gauge theory. This is what we want to do. This is like very standard. Now I will give you some two gauge condition. So two gauge condition will be some Gij equal to 0 and delta Ij Gij equal to d. See this xi, this is like d-dimensional diffeomorphism. There will be d degrees of freedom, and then there is a phi 1. So there is really d plus 1 diffeomorphism, and so I am fixing a d plus 1 condition. This is some like del I Gij equal to 0. I am making some traceless, like some divergenceless, and I am also making some traceless condition. Like I am saying this trace of g is just d, so any fluctuation will have some trace 0. This is some standard trick. Now the point is, after fixing this gauge, you also have some residual gauge. That we know in gauge theory we always have. After fixing some gauge, you also have some residual gauge. And what we find, you can systematically find this residual gauge. I don't want to go to the detail for the sake of time. I will tell you that residual gauge, this will be something xi I will be some alpha I, xi I will be some Mij xj, xi will be some lambda xi, and xi will be some 2 beta x xi minus x square beta I plus some beta j pij. Okay, so these are my residual gauge, and as you can see, these are just some CFT transformation, almost CFT transformation. This is just saying if you do this alpha, these are some constant parameter, alpha, m, lambda, and beta. There's some constant parameter, and this is just something like SO1, d plus 1 CFT transformations, and they are coming as a residual gauge after fixing these two gauges. Okay, and this is almost like SCT. The last guy is almost like SCT, but it's not. It is some field dependent. So there is another factor here, V here, and this V actually depend on your metric. So it is some field dependent transformation, which is the residual degrees of freedom here. But then you can ask whether this algebra is really SO1, d plus 1, because it is a correction. But if there is some field dependent transformation, you have to also modify your commutator. And so if you take a modified commutator, because your transformation will include the value of your field, so then you get this algebra is same as SO1, d plus 1 or the distributor isometry. So what I am claiming here, I will do this Faddeev-Popov trick. I will insert this Faddeev-Popov determinant into here, and for that I have to fix some gauge. And after fixing these two like very standard gauge, like this is saying the divergence of your metric is 0 and trace of your metric is some d, I am having this residual gauge, and the residual gauge is same as SO1, d plus 1 algebra. Okay, this is very standard. Okay, so this is a standard procedure, and yeah. No, so the point is like when you are you have to find when you are like doing this transformation, so your metric actually changes from one value to another value. So you have to like subtract that value, kind of thing. I can give you the full form that this modified commutator later. Like I'm saying, but this algebra is same as SO1, d plus 1. There is no argument about that. Okay, so now we have to fix this residual gauge also. Okay. So I will just give you the detail. So you see, like this is some translation. Okay, this is some non-compact degrees of freedom, and this is some rotation. Rotation is fine. So I am saying I am counting the non-compact degrees of freedom. Some d here, and then there is some this is some scaling. This is just 1, and then there is some SCT, which is also d. So there are some 2d plus 1 non-compact like 0 0 modes here that we have to fix. And one standard way to fix this, to fix 3 points. I am claiming that fix 3 points, x1 is 0, x1 is 0, x2 is 1, and x3 is infinity. Or you can change some coordinate, write x3 cap as some x3 by x3 whole square, and you can put this thing to 0. Now how many conditions you have here? You have 3D condition. Okay, so just I will do an algebra here. So I had SO1, d plus 1 algebra, which has like how many degrees of freedom? D plus 1, d plus 2 by 2. Now I have to fix this 2d plus 1 non-compact degrees of freedom, and I am fixing something extra. I am fixing 3D. Okay, this is something you can think, this is like in string theory, what do we do? Like in string theory, we have also this kind of problem. We fix 3 points there, 0, 1, infinity. I am doing the same thing here. Nothing like different than that. This is very standard procedure, I wanted to say. This, like writing this norm in this way is a very standard procedure. And now I am dividing it, and that will give me some d minus 1, d minus 2 by 2. This is same as some degrees of freedom on a SO d minus 1 like sphere, like these degrees of freedom. So these are some compact degrees of freedom. So we can like neglect that, like they are giving some finite volume. Even if you just integrate over, or you can just exclude them, this will not matter so much for the sake of norm. Like it will be finite. We have already got rid of all the non-compact degrees of freedom. So I have made this thing finite. Okay. So I am forgetting this. There will be some SO d minus 1 like degrees of freedom, 0 modes. I am forgetting about that. Okay, because those will be something finite case. Is everything okay? Fine? Okay.
Those will be of measure 0.
No, you can actually, when you will be doing this thing, you have this DC. So you can you restrict yourself, like you will not do this integral there. Like you restrict yourself, you don't, or you just, or maybe, like I am saying, those will not have any much effect, like it's some finite volume. So it will not have any effect. I have already got rid of all the non-compact degrees of freedom. Okay. No, it is just some SCT. It is just some SCT. Like it is some field dependent, because I have chosen this kind of gauge here. That gives me this kind of field dependent SCT. It is just another version of SCT. Its representation is different. Representation is some field dependent way, but it's still some SCT. Okay. Fine. Okay, I will just write the final form, and so with this, so I am fixing some gauge conditions there, and also I am fixing some zero modes here, and I will write the final form. I will just delete this thing. I will write the final form. Then after this, I will go to cosmological coordinate. This is just some for completeness. Okay. So I am writing this thing. Psi is something dg, d chi, dc bar, and there will be something, this guy will be there, this kappa to the power n plus n, this psi star psi will be here, this will be something delta g, this is just the psi star SI. If you remember, there is some sum over this guy. And then I have this ghost. Then I have all the delta of these gauge conditions. This will be those gauge conditions, and also these 3 gauge conditions. And now you have some Faddeev-Popov zero modes here. And you can actually set this thing 1 with some piece, with some some further calculation, you set it to 1. I just want to say this is some generic structure, and maybe there will be some C prime here, like this is like excluded the zero modes. And now I will write the same thing here, but just 1 minute. Yeah, I will write the same thing, but with some different notation. This part is all clear. This is just standard Faddeev-Popov trick, like we do in gauge theory. Nothing more than that. Like there will be some ghost action, there will be some gauge fixing condition delta, and then there is this is the standard psi star SI, psi star psi, and then this is zero mode. This is a standard speed. Now I will just write a different notation. Now you can ask, what are these x1, x2, x3 points? What are these points? You can ask this question. Now I am saying like this delta g, if you remember, this is something like CFT correlation functions times some fluctuation, then there is this integration. So these have some like integration over some x1, x2, x3 points, and you can choose one of these points like this. You fix one of the points like 0, 1, infinity, and that will give you finite results. And okay, and then I am introducing some new notation. One notation is, if you have some delta x1, delta x2 minus 1, and delta x3 hat, and say I have some function I am integrating over it, and they will be integrating over all the xi. If I fix these 3 points and then integrate, I am introducing a new notation which will be x bar. That's some notation I am saying. Okay, and then another thing I am introducing, this will be something like say q is some operator, or you can think it is some like x, that will be some dg d chi, but then there will be not the zero mode fixing, but the first 2 gauge conditions. It is like gii minus d and delta gij, and times some this Faddeev-Popov, this will be this So if you integrate without zero mode, you will get some Faddeev-Popov determinant here. This is for the non-zero ghosts, and then there will be some z mod z0 square. So I am just writing these two integrals. Okay, and with this I will write this thing with a very simpler notation. Please, if you are lost in the calculation, I am sorry for that. Please ask me a question if you are if you feel something is not clear or anything. So I am saying this thing you can write as the same thing. You can write as kappa to the power n plus kappa to the power n prime here with this guy delta g nm star delta g. So I am saying this is my compact way of writing this inner product, or the norm. Like we have to do I am just differentiating with two different things. One is like you fix some gauge, and there are no zero mode fixing here, and you multiply the corresponding Faddeev-Popov determinant everything. This is the one part, and then there is this zero mode fixing. I have separated these two procedure and have written with this notation. So this bar means we are fixing the 3 points, and this is just some gauge fixing and integrating to find some norm. Two different notations. Okay. Okay. Now I think for the sake of time, I should I should tell you what is the cosmological correlator, and just one comment here. This guy, if you look at this is almost like some QFT correlation function calculation. There's a fixing some, because in QFT we don't have this gravitational degrees of freedom, we don't have a diffusion. This is a fixed gauge, and some you can actually put some, okay, there is some Q here, I forgot to write the Q. Okay, sorry. So I am saying if you have some local correlation function here, and then it is like you're doing some calculation, a fixed gauge, and this is will be if you take some kappa goes to zero limit here, this will give me some correlation function of QFT. Okay, just one comment I wanted to tell you, this will be I have this this is my quantum gravity inner product, and if you take kappa goes to zero limit of this guy, you will get QFT inner product or QFT norm. I just want to I don't want to elaborate, but I am saying if you take this guy psi qg, okay, just 1 minute. Okay, just okay. Say okay, if you remember there is this non-gravitational psi mg. If you take the quantum gravity inner product of this guy, this will be related up to some factor volume of SO1, d plus 1 psi . So I just want to emphasize this relation, this norm is different than the QFT norm, and this is related by this volume of your de Sitter. So you can think this is some okay. So if you remember the structure of the Higuchi, the psi ng is my Higuchi state kind of thing. So it has this UG floating around. So this psi ng, this is something like some UG psi QFT, or maybe okay, you can say some kind of psi QFT. And so if you take inner product of these two guys in a QFT, if you forget all this structure, everything, if you want to study this inner product, so you can think you can always extract one group volume here. I am saying if you calculate this psi ng QFT, you can always extract a volume of de Sitter, volume of SO1, d plus 1. Because you have UG here and you will get another UG from here, and you can always redefine your field and you can extract one volume of de Sitter outside. So this inner product, the QFT inner product diverges of these guys. But what Higuchi actually, this calculation was first done by Higuchi. Higuchi told us heuristically, oh, why don't you divide by the volume, then you get a finite piece. So I am saying this quantity seems very divergent, but if you divide by this volume, then this is very well defined term. This is not diverging or anything. And this is what I want to emphasize. All this kind of thing we also got from our calculation. And we is actually solved for the full gravitational thing, and we got all these results. Okay. Yeah. Yeah, so if you remember, like we can, so these volumes naturally comes. Like we had this diff-and-Weyl. If we go into some non-gravitational limit, that diff-and-Weyl volume go to this volume of S1 quantity plus 1. Oh, okay, sorry, yeah, H, I think.
You are integrating over H, right?
Yeah, this, okay, sorry, yes, sorry.
Then,
sorry.
Sorry. So typically when we do string theory, we also sum over topologies.
Oh, okay, yes, a good point, thank you. So here we are assuming the topology is always sphere. Like we are like studying the deformed sphere. The fluctuation is around some deformed sphere. Thank you for this question. Yeah, so, okay. So this is some genetic structure, and we rediscovered the non-gravitational limit from our way. It's some very nice structure. Okay, for the sake of time, let's go to cosmological correlator. Okay, I think I have 15 minutes. Okay, I can delete all these things. Now, okay, remember that structure. That will be very important, this Q here. So as you all know, like this cosmological correlators, there are some QFT correlation functions. Okay, so we have this here, this very late time, and we have some insertions here, some local insertions here, and say I am writing this some C is some m copy of H, and say m copy of my scalar field. Okay, I am changing H and G like anything, like I sometimes using G and sometimes H, but you can think these are like almost same. Like this measure, you can think this is also one of H. Okay. So there are some chi here. So let's take a string of operators. Like these are at each point. These are very local operators. Like at each point, say y1, yn, and then there is some z1, zn. Some string of operators. This is a local operator. Now I can do this thing. Like just a minute. Yeah, I can define cosmological correlator psi. So I have the full gravitational psi, which is solution, and with this C here, C is this some string, this here. I have like removed all the indices here. So C psi here, and this is the same inner product structure here we have defined here. So I am saying this guy is some cosmological correlator. So you have some string of local operator, and you take this inner product, not this. This is because it is some QFT. This was needed when we were doing some full gravity calculation. We have to fix these zero modes. That's why this part came. But this part is something like almost like QFT. This is like fixing some gauge and doing integration over all the measure. So I am demanding this is what you should understand as some cosmological correlator. This is my definition. Okay, now these are not any gauge invariant operator. These operators, because in gravity you know, like there cannot be any like local gauge invariant operator. So either you have to lose locality or you have to lose gauge invariance. So we are losing gauge invariance here, and we are saying this is some local operator on this very late time slice, and you should understand this cosmological correlator as this inner product. Okay, is this understanding clear? Yeah, this is what we are claiming. This is what you should understand as cosmological correlator. Now, if you are very careful, you will see like these guys, like whatever is there, this Faddeev-Popov and everything, they actually these zero modes of which you did not fix here in this expression. Under the zero modes are some residual symmetry of this integrand. So under this zero mode transformation, this guy will change. This C will change under the zero mode transformation. This will change. This will also change because they are not any like invariant object. They are some local object. So this will change, but this integrand will not change anything. So the full thing under these zero modes, because we did not fix those zero modes, they will change covariantly. Under zero modes. Okay, the SCT is a bit complicated. The SCT will relate different cosmological correlator, but for the first three, the translation, the rotation and this dilatation, they will almost change like covariantly under the zero modes. Is the understanding clear? Because see, this integrand is not changing under the zero modes, but these will change. This is some local operators. If you act with some translation, this will change everything, and so this full thing will change covariantly. So I just wanted to write like how this change under translation and scaling, which will be important for us. Okay. So I am saying, okay, so I have like removed many notation here. So I want to write one precise thing here. Just 1 minute. Psi. If you have any question, please feel free to ask me. Some n m and something like. Okay, I am removing all the ij index. This is under some lambda x vector plus zeta. Okay, I'll tell you what this notation means.
So let's understand.
Yeah, sure.
So suppose we are calculating the scalar fluctuation to the scalar spectrum index.
Yeah, this so 2 chi.
Yeah, 2 chi.
Yes.
So
Chi.
according to your prescription, we still need to integrate over each
Fluctuation,
fluctuation.
yeah.
And so that seems like it's not obvious why that should match up with what we calculate in the Poincare patch, where because we are holding the background there fixed, we never actually integrate over any fluctuation.
Okay.
So why should that?
But maybe you can do.
So are you saying that this is your what is natural in your?
Yeah, natural. Yeah, for that you can also divide by the norm. Like also the okay.
You're saying that might cancel out the.
Yeah, like if you have some fluctuation, so the norm is ill-defined if you just in this prescription, the norm is ill-defined if you don't have some delta g. Like if you choose some x, like so I have this this is my state. If you only take this z0, the norm of psi is ill-defined. But if you take some delta g on top of some excitation on the vacuum, then the norm of psi is well-defined because there are some points for zero mode fixing. And so for those, I think you can also divide by the norm, and then I think this.
Has anybody done the calculation of something like a 2-point function in your language, in the language of this prescription?
Okay, I know that this my friends are doing the Ashik and Tini, they are doing it, but I don't know what they like. The final result I don't know, but I think it's something consistent. Like, okay, you are saying this is like not what we do in standard cosmological correlator.
Yeah, because there we don't integrate over the fluctuation, right? We hold the background fixed.
Yes. But
Here you are saying that even if you are calculating something like a scalar 2-point function, you still have to do
no, but okay. But you can also calculate some graviton fluctuation there, no?
Sure. But even for something as a scalar 2-point function, it's not obvious to me how the integral drops out. Integral over each drops out.
Okay. I understand your question. Okay.
Yeah.
Okay. Yeah, might be. But I'm saying. But I'm saying even if you have some like contribution from here, you can also divide by the norm of your state. If your state is some excited state, like excited state.
I think what he's saying is going to happen, that you will get this 1/omega corrections to the standard
Omega is here what like this.
large volume.
Okay.
Because if the volume went to infinity, then all the fluctuations go to zero.
Okay. I see. Okay, that might happen. Okay. I did not check that personally, but okay. Yeah, I just wanted to say this. This thing. So I'm just saying under this thing. So this notation means like this. You can think each point I am making a like this with this y and z. I am making a vector that is my x, and I am scaling that x. And some lambda is some scale, like some constant factor, and zeta is some constant translation. And with this, it will be related with some m delta and this psi C A M M X psi. Yeah, I am very close to the end, so please. Okay, I will be.
The metric fluctuations are there or not?
Yeah, there, because the C I have defined with the H. C I have defined with H. The C is some string of operators, and I am saying there are some n metric fluctuation and m matter fluctuation, and I am saying under this.
Where do you get a factor of lambda to the minus 4n or something like that?
So
H couples to the stress tensor, so the stress tensor has conformal dimension D.
yes.
And it will be 3. So sorry.
Yeah.
In case it will be 3. So do you have any information about the?
No, but it is the H, not this delta G. Like this is the field in the de Sitter. So H has conformal dimension 0. Yeah, like I am saying, because this H, this transformation of H, we have defined a diff, and then we also absorbed some Weyl factor there. So that's why like this, this H actually changes under the conformal dimension 0 here, and the matter is some delta. Yeah. Thanks for the question. Yeah. Thanks for the question. Yeah. Now this, so this is some standard translation and scaling, and I am claiming that this is what one can get. Like if you do, so I was saying that under this 0 modes, they change covariantly, and this is the covariant change of this correlation function, the cosmological correlation function. Okay, now I am very close to the end. So now what is the picture? So this x and everything, these are like some sphere coordinate here. You can think this is some sphere coordinate. And now I am saying like this is not like sphere, but on this corresponding this Euclidean plane, this where you can do some like stereographic projection or mapping here. So this x belongs to here. And now I am saying with this, if in this plane, like we are thinking on this plane here in this plane. So I will request you to look at this picture now. So let's say I have a open subset. This is some curly R, and this is my full space here, full space, and then I have this complement here. Now I am saying like given this some arbitrary choice of points, some x prime, okay, some x prime, some arbitrary choice of points here, I can always find another choice of points at, so this belongs to the full space. And for this, I will always get a choice here, x that belongs to R, the curly R, such that, such that this x prime is related with some lambda x plus zeta. So I am saying if you give me some arbitrary choice of points here in the full space, I can always map those points like the x prime with some points here at curly R with some scaling and translation. This is some geometrical fact. There is like nothing physics or anything, it's some very geometrical fact. Now look at this correlation function. Okay, now I am saying if you have some correlation function only here, only in this region, you can always map this correlation function in the full space with using this fact like the scaling and translation. Okay. This is very okay. Now, now you can say like, oh, this happens to any conformal field theory, because this is we are just using the conformal field theory. Now the catch is this conformal symmetry is there only in the vacuum of your this conformal symmetry is only for the vacuum correlation function. If you had some excitation on top of vacuum, that are not satisfying the that is not having this covariance. Okay. So now as our psi is some ZCFT, you can think this is almost behaving like different, like this is valid for all these possible psis. This is not only for vacuum. Like if you, and each of the psis is some like some ZCFT, or you can think it is kind of CFT vacuum. So for all the states, this covariance is true, and so for all types of correlator, this statement is true. So if you, my state claim is, if you have some correlation function here in a small open set, you can map these correlators to the full big space. That's my claim. Are you happy with this claim? Like this is there any fallacy or anything? Do you see anything? Okay. So now I am going to state something. So I am saying set of all correlators in any open set R will give all correlators. But if I give you all the correlators, say for a given system I give you all the correlators, then you can actually identify the state. Like I am saying I am giving all these correlators here. With this symmetry you can map to all correlators on the full space, and if we do all the correlators in the full space, that means we know the state. So we know about, we can distinguish the state if there are two different states, psi 1 and psi 2. And if we have the information like the psi 1 and psi 2 are matching everywhere, like I am saying the expectation value of different operators for psi 1 and psi 2, they are matching here, then they should match everywhere, so they should be the same state. So what I am claiming that, this I don't want to, so one can identify. So if you have some different operators, say some C psi 1 and C psi 2, sorry psi 1, some C psi 1 I am taking sandwich with this psi 1 and psi 1, if the same as some psi 2 C psi 2 for all possible like C here, like all this possible C here, then I am for C belongs to, like C is some operator on R, the curly R on the small open region, then I can identify, I can say like psi 1 equal to psi 2. I can distinguish between two states with only the information on a small open set. This is my claim. So this is the like statement of holography of information what I put, like we can identify the states with only the information on a very small region. Now what is this region? This, if you go to this picture, this is this big sphere here. So this is my Cauchy surface here, this sphere. So I am saying if you give me some information in a very small region here, like this is my sphere here. So I am saying if you give me some information on a very small open set, I know all this all the correlation function. I can identify the states. This is the statement we are putting. Okay. So, yeah.
In EDS there is something different, right? I mean, there is entanglement wedge.
Yeah, I'll come to ADS. I'll come to the full boundary. No, the point is here everything is in the boundary. I am saying if you so this is my boundary is there is nothing in the bulk. Like bulk is hollow. The de-Sitter is on the surface. So the Cauchy surface of the de-Sitter is this circle. So I am saying if you give me some information or let's say small arc here on this circle, if you give me all the correlation function, I can tell you what is the states. I'll come to the.
You made some comment about how this is different from flat space.
Yeah, I'll come to that point. Yeah, I'll come to that point. Yeah, I'll just take 5 more minutes. I'll just end by that time. Yeah. So keep the picture in mind. Okay, let me draw some other picture then. So you may ask how this picture is different than flat space and ADS. Like you cannot have some different statements for different space. Like there should be some uniform statements of holography. So if you remember, say in ADS or flat space, say I am for convenience I am drawing ADS. So the point was I have this Cauchy surface. This is my Cauchy surface, and my information was here at the boundary of your Cauchy surface. This pink line, this pink circle. So ADS is a like filled cylinder. This is my Cauchy slice. Information is here. Now, okay, let's draw the Cauchy slice. Let's take this disk and draw it differently. So here, so I am telling this is my boundary. This is like it's a boundary. This is not a sphere. Like this is a disk. This is a disk. Okay. So you see, there is this region R. Bar, and say this is my region R. If there is some region R which is like encompassing R bar, like it is, and it is the complement of this region R bar, then it has all the information. Okay, so I am writing in a different way. If in a pure state, like this R surrounds this R bar. R bar is this, R bar means its complement, then all info of R bar available to R. Okay, so I am saying the standard ADS-CFT holography you can put in this language also. Like this is some, like this is the bulk and this is the boundary and this you can think there is like there is some epsilon width of the boundary, you can also always think like that. And the point is this R is this region is complement of this region and this completely surrounds it. So you can put ADS-CFT this holography in this language, the Cauchy slice thing. And also this happens here. If you draw a sphere, this was a disk. So I am drawing again a like ball, but this is a sphere now. This is the surface of a sphere. A sphere, what was happening if I have some region R and this its complement is R bar. But now you see like R is also like surrounding R bar, and R bar is always surrounding R because it's a compact subspace now. This is a sphere. This was not the case here. This is the case here. So R and these are like complement of each other. So the point is now R has all the information of R bar, and R bar is also have all the information of R. So in this way, like these two statements of holography, they are almost like equivalent, and you can like put them in a common language here. So this is the thing. Now you can always ask like why this is happening. Like we are doing some local operator, but you like why this local operator have all the information everywhere. But if you remember, like this local operator, so we have lost the gauge invariance here. But this local operator, the expression of local operator, they are actually related to some gauge invariant non-local operator. Like you can write this expression value, you can relate this expression value with some other operator, which is some non-local. Like non-local means it is now in the full space, and it is also gauge invariant. You can always write that. So secretly, this guy, this local correlation functions, some local non-gauge invariant correlation function, this is somehow already all the information of the full space. And that's why if you calculate here only, you can get all the information. So this is some like a manifestation of this structure of this correlation function. Is there any question?
Yeah, so in order to understand this comment that you made just now, what role did quantum gravity play?
Quantum gravity plays, okay. So this psi actually is like, psi is some jet CFT, and that comes from the quantum gravity. Like if, okay, let me tell you in this way. We know for the vacuum, it was a vacuum, they have this covariance. Under the CFT, they have this covariance. But here you have some excited state, that covariance breaks. But the constraint gave you this covariance, this constraint that like in this limit, they give you this covariance. Like this actually changes like some CFT vacuum, like under, like the full thing changes like some CFT vacuum correlator. That actually is guaranteed by this quantum gravity constraint and everything. Like in a general CFT, it is not true. What I am saying, this statement is not true in any CFT, because if you just go to any excited state, it will just break. But I am saying this because all the other states are like some jet CFT that ensures this covariance. And that actually then ensures this information is only like available in a very small patch. So quantum gravity is very important for all these constructions. So and this way you can see like this is almost equivalent to the ADS-CFT construction. So if there are any question, please feel free to ask me. Then I will review and give you some brief like outlook. Yeah, sure. Boundary, you don't have a boundary. So you can think R bar is surrounding R, and also you can think R is surrounding R bar.
But in the case of these,
Yeah, you have a natural boundary. So my statement is, if there is some region which is surrounding its complement, then this region is having all the information. Then, like analogous statement here is R bar. R bar is encompassing this R, and they are complement to each other. So R bar is having all the information of R, but this is also true for the vice versa. Like R also have the information of R bar, because R is also surrounding the R bar region. Like you can go both way here, and that was not true here.
So
Yes, sure. Yeah.
Mathematically. So psi 1, if I started off by making the h and i's be restricted to this r, I could rewrite it in terms of h and chi restricted to r.
Yes, using this covariance. Because under this covariance they change very simply, and with this covariance you can just write this correlation function in a big. So I just wanted to draw some picture. Okay, just 1 minute. I think I can just draw some picture for you. Say there are some say there are some points here and some say here and say here. So I can do, say there are 3 points outside. So I can do some scaling first. So I will say there is some origin here. So I will first scale scale with respect to say origin somewhere. Say I will just do say here. Say I am doing some scaling. So under scaling everything squeezes. So these 3 points are here. Then I can do a translation. Say this is my final point. This is my A, B, C. This is my A prime, B prime, C prime, and then I am doing a translation. So this is my A double prime, B double prime, C double prime. So you see, like all the points, they are like related with these points here with some translation and scaling. So that ensures this thing, and that is ensured because psi is some ZCFT. That was actually important. Okay, so yeah, please ask me any question if you feel. Yes, sure. Yes.
This wave function is on a particular Cauchy.
Yes, wave function is particular Cauchy.
Then you are going to evolve this wave function using the Hamilton.
No. There is no evolution. There is no evolution. Everything is at very late time. All this, all this inner product, everything, all different late time. Because that's the diff-and-Weyl was in this wave function invariants on a diff-and-Weyl only at the late time slice. If you push it in finite time, those invariants are gone. So yeah. So this is the structure. This is what we propose. Now you can ask this question, like, why don't we see holography? That means something happening in some Andromeda galaxy or something. You can because that's what this our proposal says. No? You have all the information in a very small open region. Why don't we see holography around us? So you can ask this.
But you have to be on the same.
Yeah, same. Yeah. Okay.
Andromeda and us, we are not on the same.
Okay. Let's say something on the same time slice, but far away. Say, I am saying on the same Cauchy slice, but far away. But still, we don't have the information. Like we see, I am saying this. What we are stating here, we don't see this holography information around us.
What does the statement mean? So how do we know that we don't have the holography of information? What does it mean?
Okay. I'm saying in this way, like these things are valid, on top of the vacuum. All this construction we are doing on top of the vacuum. If there is some excited state that I was telling you, then you can hide the effect of the constraints. So what I am telling you that we solar system, everything, all this galaxy, there are some highly excited energy, like high energy excited state, and so you can hide this constraint up to some part in the perturbation theory. So you may not see these constraints. If you are around some high energy state, you may not see this effect. What I am saying. So I am saying these statements are valid around vacuum. We have some vacuum structure, and we have explicitly our excitation was on the top of the vacuum. We have all this small fluctuation basis, everything. I am saying that our statement of holography is not valid. Like I'm not saying it's not valid. I am saying it's not very manifest if you have some high energy excited state. Is this statement do you agree with this statement?
I'm trying to understand this. So, suppose I wanted to devise a test whether this principle is valid or not.
Yes. Okay. Okay. So.
Seems like a very non-trivial.
Yeah, it seems like very non-trivial. Like you can, I think you can always define some protocol. Like I say, like whether like how much information you can get perturbatively, like around vacuum. You can devise some protocol. But okay, experimentally I don't know. Like.
So maybe I'm sure I understood the comment that we don't see the
No, okay. I wanted to say like, okay. Now I am saying like we may not see. Okay, let me correct my statement. I am saying we may not see, like if we have some. So this holography of statement, holography information, this was valid around vacuum and like if there is no high energy excited state, like because if there is some high excited state, we can trace everything with that state. And then this effect of this this constant, because these are also manifestation of the constant. This everything, all this statement was a manifestation of these constants. That's gave us this structure. But if you have some like excitation and if you are dressing around that excitation, you may not see these effects.
But I thought you said that there are two complementary pictures.
Yeah, two complementary. Yeah, there are two complementary pictures. But I'm saying this like in our picture there is no high energy excited any state. Like this picture does not have. But I am saying if we had some kind of high energy excited state or some like some very massive particle geodesic something, then you can hide these effects up to in the perturbation order.
Hide what effects?
This holographic effects. We may not see this like this information of R is actually like sufficient to determine all the correlation function. Like this statement what I put here, like the information of R is sufficient to find all the correlation function, this statement will break. That's I am claiming.
So
Yeah, sure. Yeah.
the size of the sphere is sorry. So this is the sphere
A sphere at very late time.
at
Yeah, we still don't. Yeah,
and the size of the sphere is infinite.
it's very large, very large. Yeah. So yeah, you may say like we have not entered that phase now. Maybe you can say that's also true, but like we did not enter into that phase now.
What can we do experimentally to measure this?
That's why he said that.
Yeah. This is some, okay, this is some theoretical statement. Okay, I have to think.
Suppose there is holography, how can we measure?
Okay.
No, but
Let me-
just to understand this picture again, so
Uh-huh.
there is the way that you've drawn it. It seems like we are considering two different times. One where the size of the sphere is R, and the other where the size of the sphere is not R.
No. This is the one sphere.
So there's one sphere and then subregion.
Subregion. This is subregion of the region. Like this is say where we are living, and this is the complement of the region. And I am saying like the statement that guarantees.
The surface of the sphere.
Yeah. This is the sphere, like not the ball.
Okay.
This is the sphere, not the ball. Yeah. Like I'm saying, this R is my like if you take a ball, this is some region here. Yeah. Everything is compact here. I'm saying there is a difference between this and this. So this.
So, but that would seem like this is saying that if I did not look at very distant galaxies, but I actually looked at correlations between nearby galaxies.
Yeah, that will determine all
It
the.
should be the same. Somehow it should be the same, replicated
Yeah,
by
that-
observations of distant galaxies.
Yes.
That is what
Yeah. Like okay. Good. Yeah. Thanks for this. Thanks for going for that picture. Yeah. So you're saying like if we have this, if we have some observer here, we have some meta observer, and we are say this is my. So this you can think is some big sphere. Like this is some big sphere. So what we are saying like if you calculate some correlation function here, and that will give you all the correlation function in the full space. That is one nice way to put it. Yeah. Thanks. That is one nice way to put it. Thanks. I forgot this. So as I was saying in the beginning, like this statement, whatever we are doing, it is valid for meta observer. Like our observer is not sitting inside this data. So like say this is the inflation, like where the inflation ended, some surface, and what our construction is saying, like if you have some small region, so this is like a sphere, and so I am saying if you have some small region here, that is enough to determine all the correlation function everywhere in this surface. Yeah, that's one way to say it. So maybe if you study this cosmological correlator, maybe you can say.
Can I say that this observable is what we are, and this inflation time is somehow very far in the past?
Yeah, but this is only one single slice. This is only single slice. Everything is valid in a single slice. So I think it's thanks for this statement. This is more precise way to say, like, to check these things. Yeah, thanks.
So are you thinking of devising? I mean, it seems like something that you should be able to check by studying the CMP spectrum.
But there is some problem with relating. I think the standard cosmological correlator. I think that some of you mentioned, like they are studying some QFT correlators basically, the standard cosmological correlators. But we are starting from some gravity and trying to calculate something QFT. So there we should relate. I think one first step is to relate this thing nicely. Then I think maybe there is something is possible. Yeah.
We went back to ADS space and we tried to do everything in Poincaré coordinates.
Okay.
Poincaré coordinates.
Yes.
Then there is still a statement about
holography.
Holography, right? I mean, just holography of information.
Yes. Poincaré patch. Yeah, they're like. Let me think. Yeah, I think yes, but okay. I have not seen any like whether this the same principle that what I am saying, whether it is done anywhere, I don't know, but I think it will be still manifest. But why do you ask that?
Because then if this principle is valid,
for ADS Poincaré, then you can.
Consider space, and you can directly relate it to what people actually compute.
Okay. I see.
I mean, there is no. I think you could just say that why isn't this the correct way of computing correlation?
No, this is okay. This is very. I want to say we started from very generic principle and like we assume if there is some gravitational effect that will be this that will be counted in this way.
No, I'm not saying that this is not.
Okay. This is.
Why is this not?
Okay.
The correct way of
Okay. Yeah, this is there is a standard ADS-CFT holography, but also you can write that statement of ADS-CFT holography in a statement on a Cauchy slice. Like I am saying, all the information of this full bulk Cauchy slice is available in its boundary, and here also like all the information of the full Cauchy slice is available in this open region. No. I am saying like it will not depend. I am saying in a full quantum gravity version, like all this psi, all this psi will have this covariance. If you take any correlation function with any psi, that will be changed under covariantly, and that gave me this relation. This relation that I got that came from this covariance of any states. It's not any only ground state, but I am saying like it's not any CFT. Like you can think like this is some CFT symmetry. We just exploited some CFT symmetry, but it's not true for any CFT. It is only true for this de system, because in CFT system only ground state correlation function or vacuum correlation function will change in this way. If you put some excitation on top of this ground state, the covariance will break, so you cannot write this kind of statement for a CFT on a sphere. Say you are studying a CFT on a sphere, you will not have this statement. So it is very much quantum gravity like statement. Okay, just I want to summarize. I just take 2 minutes. Okay, it's already very late. I'm sorry. Okay, so okay, just I want to sum. So what I claimed, and I will like we got that full states. The first lecture we got these full states. Those are in the form of e⁻⁻ and then we analyzed all the structure of jet. I said this is almost like some CFT partition function, like quote unquote CFT, and then we got some another basis for that was useful to analyze the non-gravitational effect, etc. And then in this today mainly we defined some inner product of this psi, and we found that and we also devised some cosmological correlator in our way, cosmo correlator. and we found like this cosmocorrelator are like satisfying some nice property, and so that it can be determined from a very small region. So, and this is what we are calling holography. And okay, it's yeah, we have to make it more manifest, like how to test these things. But there are some important future directions apart from this thing I wanted to mention. Just give me 1 more minute, I will be done with that. So like one question is that, okay, obviously they want to like direct question to relate with this cosmological correlator more directly, like make it precise. Our cosmological correlator, our formalism. We have to make this connection more precise. That's I think my friends are doing it. Now, there are some other directions apart from this cosmology directions, which is very interesting from a field theory perspective. Like one thing is that, like this is the leading order solution. Okay. Now, if you go to one subleading order, like everything is leading order, you will get some solution. Now, the point is whether these solutions will be isomorphic to the solution we got, whether the Hilbert. So, my question is something like, okay, I think it's very raw. I don't know whether it's the right question to ask in de Sitter, like whether the de Sitter space is unitary. Like, I mean, like if you have some inner product structure here, can you have this inner product structure is isomorphic to some inner product defined in this slice? Like, can I ask these questions? This is, I think, very open question. I don't know. Maybe you can, if you have some observer, you can like write this question in that precise way. But I don't know whether this question has a good understanding altogether. So what I'm saying, like whether this Hilbert space we have defined here, this Hilbert space have some unitary evolution from here to here, and if there is unitary, the question will be with respect to what Hamiltonian, because Hamiltonian is 0. So maybe it is not unitary. Like this inner product here and inner product here, they are not isomorphic to each other. That's one question. And also, like forget inner product, you can also write the states here. So I'm not saying you are going from here to very finite time, but say a little bit. Then in the Hamiltonian constant, there are some terms which is called like t bar terms or t squared deformation terms. So you replace all the pi with the stress tensor, then you will get all this. If people study this t bar deformed CFT or t squared deformed CFT, there will be similar term in Hamiltonian constant. So there are some group of people in Cambridge and other people like Gonzalo, Rifat, they actually study this thing. They claim like what we have this e to the power is jet. They are saying it will be some is, but it is some jet QFT, and this jet QFT will be some TT bar deformed jet CFT. There's a claim, but my understanding is we have to make it more precise. It is not like I do not understand it very much, but one good idea is to relate these things like the finite side, not finite, maybe some perturbation around the infinite, whether you can make this Hilbert very precise. So this is one like important like direction. Another thing is like Chern-Simons theory. So there is this the old paper by Witten which claims like you can write this de Sitter quantum gravity without matter with some Chern-Simons theory with some gauge group SL2C. Now here what we have done, we have quantized first, then we impose the constraints. We went to a wave function basis everything, then we impose the constant and got the solution. Now in the Chern-Simons language, what you do, you without matter, it is very trivial. Like there is nothing, no graviton. Also it is on 3D, no graviton, excitation, anything. Now the question is, you can go to the classical phase space first, and then you can quantize. So the classical phase space, when you are writing that thing, you already have imposed the constant, kind of. So that is another way of doing this thing. And now the question is whether, and I think Witten has written some solutions there. But now the question is we have to match that solutions by Witten to our solutions and whether these will be like consistent. There is some recent paper by in this direction, Lorentz and his collaborators, Lorentz, Scott Collier. I think they have recently like studied this thing and they are writing in terms of some. So this Hilbert space of this SL2C Chern-Simons theory, they are writing it as some like complex Liouville theory something in the world sheet, and I think there are some sets of paper. It will be coming. Well, I think they announced some paper, but it will be coming recently. So I think they already have some understanding in this direction. So yeah, and maybe maybe also one question will be like related to this, whether you have some classical solutions, like whether you have some classical solutions which obey the constant somehow and then you quantize. Like it will be, I think, similar to this problem also, but it's another important question to ask. So these are, so one big question is like related to the cosmology, that is the main question, but these are some side questions which will be interesting from a field theoretic perspective. So here I want to stop. Okay, thank you very much for for being here. Okay, so okay, sure. Okay, sure. I got also very good questions. It will. Okay, so if you have any question, please ask me.
So is your last comment related to whether each of these different wave functions can be correlated with the classical metric?
Yeah, like if there's some like some coherent state kind of thing, coherent state like which somehow have all the classical configuration. But yeah, that's the one important important way to see this picture. But also there will be this, but this problem is also very interesting because this will be very precise. Like all people know all this low dimensional theory very like precisely, very concretely, and so yeah. Oh, that's true. That's true. That's very much true. Yeah, because there is no graviton. There's no graviton anything. So you cannot write cosmological correlator. I agree with you. But yeah, from a field theory, I think it's a very interesting problem. Type problem, a very good type problem. And yeah, and also this is also, I think, because this T-square deformation, what people study actually, there is some very certainties about this TT T-square deformation. There's energy go to complex number, etc. So I think the general understanding is very fuzzy. Like what people claim as a holographic dual, that is actually give you some complex energy. So people have different proposals for that. But yeah, it will be nice to understand this thing also. So yeah. Okay. Thank you.